So, I have a favorite determinant, but before I swoon over it, I believe it is good etiquette to establish what I think makes a determinant good in the first place. First, the determinant should be computable with a relatively simple formula. This formula should be easier to compute than calculating the whole determinant. Second, the computed value shouldn't always be zero, and if the answer is zero, then that should tell us something. Finally, the determinant should mean something just beyond the symbols and the formula. That is, it should have an interpretation connecting it to some other aspect of math. So here is the Vandermonde determinant. It is the determinant of an n by n matrix. In the top row, we put all ones. In the second row, we put the variables x1, x2, x3 until xn. In the third row, we put squares of those variables. In the fourth row, we put cubes of all the variables. And we keep increasing the power of the variables in each row until we put the n minus 1 powers of each variable in the nth row. So the entry in row R and column C is xc to the power r minus 1. So is it easy to compute? You bet. Take the last variable and make terms by subtracting the other variables from it. Then take the second to last variable and subtract variables from it which are to the left of it. Do the same for the rest. The determinant is equal to the product of all the terms we got, which is a nifty little formula. We denote this Vandermonde determinant by v of x1, x2 up until xn, and it's equal to this formula, where we take the product over all terms xi minus xj, where j is smaller than I. I won't prove the formula in the video, so I will leave the details and links to some other videos which do so in the description. Now, what about the second condition? When v is 0, it means that the product is 0, and so it means that at least one of the terms in the product is 0. And this tells us that two of our variables take the same value. You can see this from the determinant 2 as two columns are the same, which would make the determinant 0. Other than the value of a determinant, an important aspect is its sign. In general, when you swap two rows of the determinant, its sign becomes negative of what you started with. In our case, swapping columns is the same as interchanging variables, which we can also see just with the formula. If I were to swap x2 with x4, then the only affected terms will be these ones. These terms swap with each other, so there's no sign change. This term becomes negative, and so does this term, leaving us with a net positive. So the only term that contributes to the sign is x4 minus x2, which becomes x2 minus x4, the negative of the original. All of these fascinating properties are mere abstract curiosities, if not for the broader context these objects appear in. If you have n points, then you can use the Vandermonde to find the n-degree polynomial that passes through those points. This process is called polynomial interpolation. Then there is the Wronskian, a cousin of the Vandermonde, which is used in differential equations to find whether you have a complete set of solutions. The entry in row R and column C is the r minus 1 derivative of fc, and we care about whether the determinant is 0. But my interest lies in combinatorics, and so it's time for some fun pictures. A function is called antisymmetric if when you swap two of its variables, the new function you get is the negative of the old one. Here's an example of an antisymmetric function, and you can see that swapping x and y makes it negative. In the general case, if we swap the variables x1 and x2 and then set them equal to each other, we get that something must be equal to the negative of itself. If this function is not 0, then 1 is equal to minus 1, which is mostly false, so this function must be 0. As x1 equal to x2 is a root of this function, this means that f is divisible by x1 minus x2. Repeating this for all pairs xi and xj will tell us that f is actually divisible by, you guessed it, the Vandermonde. The Vandermonde thus is the most fundamental antisymmetric function. Dividing an antisymmetric function by another actually cancels out the antisymmetry, making the resulting function a symmetric function. So, swapping any two variables preserves the function. Let's start with an antisymmetric function that looks like a souped-up version of the Vandermonde. If you have h1, h2, h3, and so on in a strict increasing order, then we make the determinant where the top row is all variables to the power h1, the next row is all variables to the power h2, and so on until the last row is all variables to the power hn. The Vandermonde is a special case of this guy, with h1 equal to 0, h2 equal to 1, and so on until hn equals n minus 1. So what is the symmetric function that we get by dividing these two determinants? Hang on tight. I'm going to give you the answer without proof. But gosh, is it beautiful. I'll use the example where the values of h1, h2, h3, h4, and h5 are 2, 3, 6, 7, and 9 respectively. First step, we start by laying h1 boxes. Then we place h2 minus 1 boxes above it. Then h3 minus 2 boxes above that. Then h4 minus 3 boxes. And finally in the top row, we place h5 minus 4 boxes. I will fill these boxes with numbers according to two rules. The numbers should increase or be equal along rows, but they should strictly increase down the columns. In this example filling, we see that in each row the values increase and are sometimes constant, but down the columns they are always increasing. We call this filling a tableau, and we can read off a monomial from it. Count how many 1s appear and put that in the power of x1. Then count how many 2s appear and put that in the power of x2. Do this for 3s, 4s, and 5s. And you got yourself a content monomial of this tableau. If we fix a shape and make all tableau on it, write out their monomials, add them up, then what we get is called the Schur function of that shape. I'll write this as S of h1, h2, h3, h4, h5. You should try computing the Schur function for this small example just to get a hang of it. And of course, the crazy part is that this determinant ratio we talked about, that is equal to S of h1, h2, and so on until hn. This determinant ended up just becoming this little problem about filling numbers in boxes. And I find that amazing. I haven't talked about the proof or why the Schur function the way we defined is even symmetric, but I will leave some references in the description if you're interested. Schur functions connect ideas from geometry, representation theory, and give rise to some beautiful combinatorics. The pictorial model of these Vandermonde-like determinants is called an abacus. Yes, with beads and runners and all. Studying how beads move around and bump into each other is how we prove the identity I showed, and many others. Maybe I'll make a video on the abacus someday. Who knows? Thanks for listening to me ramble about my favorite determinant and the combinatorics that comes along with it. Do you have a favorite determinant? Let me know below in the comments. I'm sure my determinant can beat up your determinant. Thanks for watching.